the squeeze theorem is actually a fairly simple theorem, straightforward theorem, in that if we can trap some function in between two other functions, so for example, we can trap the g function in between an upper function h and a lower function f. Okay, so if we can trap that function between those two values, and we can if we can squeeze the h function down to a limit and the f function down to that same limit, what that means is if I can pinch it from the top and pinch it from the bottom to the same limit, the middle function must be that same limit, and we can make that conclusion. Okay, so the limit as f of x or h of x approaches a equals the limit L, this y coordinate here. We know that the limit of the lower function f of x as it approaches a equals the same limit but from the bottom, and we know that the condition is that this g is always squeezed in between. Then we know, regardless of whether we can evaluate, we know how to evaluate that or not, we know it must have the same limit. So an example is this. We have this sine x over x, and as x goes to infinity, we have a bit of a problem, because sine of infinity can't be defined, okay? Because we just know that it's just going to bounce between -1 and +1. So that's a bit of a problem. Sine x can't be defined. However, we can squeeze the sine x over x between two functions, because we know that the sine x has to be bigger than -1. So -1 over x must be smaller than sine x over x, or equal to at the worst. And same from the top, sine x can't be bigger than 1, so sine x over x must be smaller than or equal to 1 over x. So what then we can do is we can squeeze the sine x over x function between those two values. Okay, so if I take that the lower one, which is in green here, so that lower function is in green, it's gonna, as we go to infinity, it's gonna go to tend towards 0, and from above, we can squeeze it with the 1 over x function. This is going down to 0. So as x goes to infinity, it's going to get squeezed in between, and sine x over x is going to end up equaling 0. So it looks like this. So, and I'll show you the graph of this. So it actually is going to kind of go like this, and basically get squeezed in there at 0 as it goes out to infinity. Okay? So what we can do then is we can just say this. So we know that the lower limit is going to be, so the limit as x goes to infinity of -1 over x equals 0. Okay, we know that the sine x over x is always going to be less than or greater than or equal to that. And over from above, we know that the limit as x goes to infinity of 1 over x is equal to 0. So we know that these two functions squeeze that sine x over x. So the limit as, I should have written this as a limit as x goes to infinity of sine x over x okay, so then we can make that conclusion that this must be equal to 0. So we can make the conclusion that sine x over x, the limit as x goes to infinity of sine x over x is equal to 0. Okay, so this is our squeeze theorem. We squeeze this function in between an upper and lower function. So another example here would be this one here, where we have this x squared times 1 over sine x as x goes to 0 from the positive side. This is becoming sine to the infinity. Okay, that's a problem, okay, because we don't know what sine to infinity is. However, what we can do is we can say that this function, this whole function, must be squeezed between x squared times 1, so where this is equal to 1, that's the greatest value that it can be, And this is also has to be squeezed between x squared times negative 1, because that's the lowest value that it can be. So then we're going to set up this limit. Okay, we know that negative x squared must be greater than or equal to our blue function here, which is a x squared sine 1 over x. And we know that from the top, we know that that function must be less than positive x squared. So we can then apply a limit here. We know that the limit as x goes to 0 from the positive of negative x squared equals 0. And we know that is less than the limit as x goes to 0 from the positive of x squared sine 1 over x. And we know that that must be less than the limit as x goes to 0 to the positive side of positive x squared, which is also equal to 0. By squeezing it like this, we now can make the statement, well, if that's equal to 0, lower bound's equal to 0, upper bound's equal to 0, well, this function must also be equal to 0. Okay, so there's my statement, and it's through squeezing it between those two functions, the upper bound of that function and the lower bound of that function, you can see as it goes to 0, it squeezes to 0. Okay, and so here's another one here where we know that as x goes to 0, this has to be at the biggest e to the power negative 1, or sorry, at largest e to the power 1, at the smallest e to the power negative 1. So we can then squeeze this function in this way. Okay, so I'm going to have an lower bound. So we're going to say that x squared e to the negative 1. We know that this function here, we'll do it in blue. We know that this function x squared e to the sine 1 over x, we know that it must be bigger, because again, this sine value can't grow beyond negative 1. And we can say also that we can squeeze this one from the upper bound, where this e function at the greatest value of sine is going to be equal to 1. So we can squeeze this again between these two values. So as x approaches 0, we know that we can say the limit as x approaches 0 from the positive side of x squared divided by e, well, that's equal to 0. And we know that that must be smaller than the limit as x goes to positive 1 of x squared e to the sine 1 over x. And we know that that limit must be smaller than, as x goes to 0 from the positive side, e to the x squared. Okay? And this is going to be equal to 0 as well. So from that we can conclude that since they're both squeezing to 0, we know that the limit as x goes to 0 from the positive side of x squared e to the sine 1 over x, that must be equal to 0. Okay? And we can show this on a graph as well.